Welcome back, scholars. This is the second video in a series where we will review all of the most important details about functions before you head to AP Calculus. Let's get started. Last time we defined a function as a correspondence between two distinct sets, the input set, which we called the domain, and the set of outputs, which we called the range. In this lesson, we'll focus heavily on the domain or the input set. In general, a function's domain can be stated explicitly using set builder notation, an inequality, or interval notation. It is also possible that a function's domain is simply implied. For example, if we have the function f of x equals the absolute value of x, in theory, there's no real number that we couldn't find the absolute value of. However, adjacent to the function rule, we see the inequality x is less than 0. This would be considered an explicitly stated domain, where we are kind of overriding what we implicitly assume from the function rule. Just below, we have g of x equals the square root of x. This time there is no explicit domain given, so we consider the set of possible inputs given the operations involved in the function rule. Since we will not have a real number output with any inputs that are negative, the implicit domain here will have to be x is greater than or equal to 0. There are a few ways of representing domain. We can use inequalities, which work really nicely when the domain is unbounded on the left or right. However, more complicated domains could benefit from the use of interval notation. With interval notation, we include the lower and upper endpoints separated by a comma, similar to the way that we write an ordered pair. Capping the left and right hand endpoints, we use either a square bracket, which includes that endpoint as part of the set, or parentheses, which excludes that endpoint from the set. We can join together multiple intervals using the union symbol. With interval notation, we are essentially shrinking the number line down to the points that are relevant for that function, so it should read from left to right or from the lowest values to the highest values. Let's practice finding the implicit domain for a few different functions. Starting on the left, I have f of x equals the square root of 9 minus 2x. To begin, I'll think about any restrictions involved with the function rule. We will get a non-real number output if we take the square root of a negative number with any even root radical. So we'll want to find the set of numbers where 9 minus 2x is greater than or equal to 0. I'll set up this inequality. After dividing both sides by negative 2 and reflecting the inequality, we get x is less than or equal to 9/2. That means that the domain is negative infinity to 9/2 inclusive. In the middle, I have a rational function, h of x equals x minus 1 over 2x squared minus 32. This time, our restriction is with the denominator. I cannot divide by 0 and get a real number result. That means that 2x squared minus 32 must not equal 0. Well, it's easier to just set this expression equal to 0 because there are only up to 2 values of x that lead to a 0 result. This is a second-degree polynomial, and by the fundamental theorem of algebra, that means that this polynomial has exactly 2 roots. So I'll set up 2x squared minus 32 equals 0 and solve by factoring. I see a difference of 2 squares here in 2 unique roots, x equals negative 4 and x equals 4. So our domain will be all real numbers except x equals negative 4 and x equals 4. To write this using interval notation, I'll go from negative infinity to negative 4, union, negative 4 to 4, union 4 to positive infinity. All the way on the right, I have g of x equals the cube root of x minus 1. This time we have no restrictions for our inputs based on the function rule. Unlike even index radicals, we can take the cube root of a negative input and get a real number result. So my domain this time will be all real numbers or, using interval notation, negative infinity to positive infinity. We can find domain and range using a graph as well. Starting on the far left, I have a piecewise defined function which includes 2 jump discontinuities. The open circle means we exclude that point, while the closed circle is meant to indicate that we include that point. I like to think of this like empty or filled seats at a stadium. The arrows pointing left and right indicate end behavior towards positive infinity. For domain, we have negative infinity to positive infinity. For range, we have a minimum value of negative 6 and no upper bound, so positive infinity. In the middle, we have a rational function with 1 discontinuity, which is classified as a vertical asymptote. In our equation, this will show up as an excluded value from our domain at x equals 0. There are no holes visible, and we see end behavior tending towards the horizontal asymptote on the left and right-hand sides. So it's safe to say that the domain will be negative infinity to 0, union 0 to infinity. The range will actually be the same this time. On the right-hand side, we have another piecewise defined function, this time demonstrating a couple of point discontinuities. Those open holes indicate that those points are excluded from the domain and range of this function. The lack of arrows on the ends of the curve indicate that this function is shown in its entirety within this graphing window. For domain, we have -8 to 0, union 0 to 4. Note the use of parentheses and square brackets at the appropriate endpoints here with both the domain and the range. Rarely are functions used in isolation. It's very common to perform operations such as addition, subtraction, multiplication, and division with functions, as well as to compose two or more functions. We'll start by just looking quickly at how basic operations with functions work. In general, the process is the same as operations with polynomials, but depending on the type of functions present, you may also need to do some work with rational expressions or other types of expressions. The notation here may be split up as it is with f of x plus g of x. Or it may be shown with the function names in the intended operation housed in their own group of parentheses. Pay close attention to subtraction. You'll need to subtract the entire function, not just the first term. Also, take care with division, because you'll want to factor the numerator and denominator to reduce to lowest terms if possible. The result of operating with two functions is an entirely new function. In the case of addition, subtraction, and multiplication, the resulting function's domain will be the intersection of the domains of the originating functions. Recall from geometry that the intersection of two sets are the elements that the two sets have shared or in common. As is always the case, with division you'll want to ensure that you analyze the resulting function to determine what value or values will be excluded from the domain to ensure that you're not dividing by zero. Composing functions is a process where the output of one function serves as the input for another function. This is sort of the premise of an assembly line. The notation for this type of operation is an open circle. We read this out loud as f of g or f composed with g. I like to use exaggerated parentheses here, showing the first function as the input for the second function in the composition. Here's a quick visual illustration of what is happening mathematically. We take an input x, and we feed it into a function, say g of x. We have an output from that function, which then goes directly into an additional function, we'll say function f. Then you have a final output or result. Let's practice with a couple of compositions. Starting on the left, we're going to use the given functions f of x and g of x to perform the composition f of g. This means that we're going to use the entire function g as the input for the function f. I'll grab the function rule for f. That's 1 over x minus 1, and I'll replace the input x with the entire function rule for g, which is 1 over x. This creates a sort of complicated denominator, but it's easy enough to simplify in one or two steps. The result is the new function x over 1 minus x. The domain will be all real numbers given that x is not equal to 1. Looking over on the right, we're using the same two functions, but this time we're composing g with f. This time we're going to use the function rule for g and replace the input with the function rule for f. So I'll take 1 over x and replace x with 1 over x minus 1. I'll take advantage of the fact that dividing by 1 over x minus 1 is the same as multiplying by its reciprocal. This will simplify to just x minus 1. Note that the domain restriction is still in place. We still have to exclude that positive 1 because the original expression was a rational expression dividing by x before we reduced to lowest terms. Looking back to the results of our example, we see that the composition of two functions does not appear to be commutative. We saw in the case of f composed with g, we have a resulting function of x over 1 minus x. When we compose g with f, on the other hand, our resulting function was x minus 1. So again, it appears that the composition of two functions is not commutative. In other words, order does matter. Looking at the notation, the inner function receives the input first. The outer function, on the other hand, uses the output of the inner function. Here's a few ways that can appear. F composed with g would use g as the input for the function f, where g composed with f would use f as the input for the function g. That wraps up our second look at function concepts. Next time we'll look at parent functions and their transformations. See you then.